Hi guys, it's Mrs. Allison. Today we are going to talk about linearization, but before we do that, I would like you to try this optimization problem. So hit pause, try it, and then come back and check your work. All right, so this one says, what is the maximum slope of f of x equals 2/3 minus 2x minus x squared minus 1/3 x cubed? So we know that anytime we see one of these maximize and minimize problems, or finding the maximum minimum, we need to write an equation for slope. Well, let's think about what the slope might look like for this equation. Well, the slope for this equation would be the first derivative. So the first derivative of this is going to be equal to -2 minus 2x minus x squared. Okay? So that's the first derivative. This is the slope. This is what we're maximizing. Now here's the tricky part. If I want to maximize this, I still need to take the derivative. So to maximize the slope, I need the critical numbers. I need to take the derivative of the slope. So what that means is I'm actually looking for the second derivative here. So I'm going to go ahead and take the second derivative, and we get -2 minus 2x is my second derivative, or the derivative of the equation I'm trying to maximize. And if I find my critical numbers here, we get that 0 equals -2 minus 2x. So 2x equals -2, which means x equals -1. And if I go and plug this in just to verify, and then we can talk about domain. If I plug this in and I plug in -1 into the second derivative, which is the derivative of what I'm trying to maximize, I will get a positive number here if I plug in, say, -2. -2 will give me a positive number, therefore my slope function is increasing. And if I plug in, say, something like 0, we get a negative number, and therefore my slope function is decreasing, which means that at -1, when x equals -1, we have a maximum slope. But what is the maximum slope? Well, if I want to actually find the slope, I am going to plug in -1 into that derivative equation. So we get -2 minus 2 times -1 minus -1 squared, which gives me -2 plus 2 minus 1. So I get the slope would be -1. So the max slope, since that's what it's asking, the max slope is -1. How'd you do? Kind of a fun optimization problem that's a little bit different than some of the other ones we've looked at. Okay, well, today we are going to talk about linearization. You guys, there's actually a couple different names that you could hear this concept called. You could call it tangent line approximation, local linearization, just linearization. But here's what it is. Sometimes it is impossible or really, really difficult to find the value of a function, okay? So if we can use some of the ideas of calculus, like the value of the slope of the tangent, we can use that to approximate the values that are close by that. So very close by is sometimes called a local linearization. So for example, if we have some crazy curve that's happening, okay, who knows what the rest of the graph look like? Just go with this for just a second. And I find the tangent line, we'll call that tangent, just pretend. But let's say I want to know what's happening right here on the original function. Well, I can find out what's happening right there on the tangent line and be really close to it, okay? Really, really close. Linear approximation is an awesome application of derivatives. And once we get used to it, there's some pretty cool things you could do. For example, you could, without much effort, calculate things like the cube root of 70 without a calculator. Pretty impressive, right? Okay, so if a function, let's scroll just a little bit. If a function f of x is differentiable at x equals c, we say then that it is locally, oops, my goodness, I'm spelling weird today, locally linear at x equals c. What this means is we can use the equation of the tangent line at x equals c to approximate f of x values close to x equals c. Well, how do we do that? Okay, so here's how we're going to do that. First of all, the first thing that we're going to do is we are going to find the equation of the tangent line at a nice point, at a nice center, maybe the point C, f of c. Okay, if we do that, the tangent line looks like this, or the equation looks like this. Y minus f of c, so y minus the y value, equals the slope times x minus the x value. Okay? Keep in mind this is going back to point slope form. If you remember the idea of point slope form, y minus the y value, the point, equals m times x minus the x value, or the point. So if you look at this, this is really the same equation. Instead of m, we've put what the slope is at that point. Now, one type of form we haven't really talked about in this class, and I'm not actually sure how much you may have been addressed this in honors trig pre-calc, but there is something called Taylor form. And some people prefer Taylor form, and sometimes you may have seen Taylor form written and not known that's what it was called. But Taylor form looks like this. It's a y equals equation, but it's not in slope-intercept form. It's not y equals mx plus b. It really is just point slope form that adds back in the f of c to the other side of the equation. Sometimes we put it in front, sometimes we put it at the end. So you could see it either written f of c plus the derivative at c. Okay, so you could see it written either way. So you can see that all we've really done is taken this y minus the y term and moved it over to the other side. Well, then what we're going to do is we're going to use our equation to approximate f of a. Now, be careful with notation. F of a is equal to an approximation of the linear function. So here's what it actually looks like. We know that anytime we talk about f of x, some function evaluated at x, it's going to be approximate to the local linearization of that function, which is f of a plus the derivative or the slope evaluated at a times x minus a. Okay? Now, sometimes it's important to know if what we're estimating is actually an overestimate or an underestimate, or an over approximation or under approximation. And all of that is based on the concavity of the function at x equals c. So if we have a curve, if this is my original function, we'll pretend that's straight. Okay? If this is my original function, and I draw any tangent line along this function, man, nothing is straight tonight. If I draw any tangent line, pretend it's straight, people, any tangent line along this point, okay? Anywhere along this line is going to be underneath my curve, and therefore my linear approximation under approximates this. It means that the value that I find is actually just a little bit below what it could be. Whereas if my function is concave down, So if my function's concave down, and maybe it's not a parabola, maybe it's just concave down, and I draw a tangent line, any tangent line that I draw along this line is going to be above the curve. And therefore, any point that I use as an approximation is going to be an over approximation. Let's use the same verbiage. Over approximates. It over approximates the value of that function. So knowing the concavity can really help us with this problem. So let's look at an example. In this first example, it says, if 2, negative 2 is a point on the graph of x squared plus y squared plus 2y equals 4, use the equation of a tangent line passing through the point 2, negative 2 to approximate a y coordinate when the x coordinate is 2.1, or when the x coordinate is 1.9. Okay, well, here's a visual of this. So we know that this happens to be a circle. It's a circle whose y value has been shifted down 2, so it's not centered at the origin. It's centered, the x value is at the origin, the y value is down 2. And it says that the point 2, negative 2 is the point on the graph. And we're going to use the tangent line passing through that point to approximate a y coordinate. For those of you wanting to know how I know that's a circle, if you think back to your conic sections, and it's been a while, when we do conic sections, we would complete the square. So x squared is completed. Y squared, we would, if we add 1 to both sides, we'd get x squared plus y squared on this side, but I'd need to add 1 to the other side, so we'd get x squared plus y squared equals 5. And because I know that that happens to be the equation of a circle, remember the equation of a circle is x minus h squared plus y minus k squared equals r squared. So it looks like the equation of a circle. That's how I know. I do think I said I shifted down 2, but I meant down 1. Anyway, that's just a side note. Okay, so let's look at what we do with this problem. The first thing that we're going to need to do is we need to find the equation of the tangent line. Okay, but in order to find the equation of a tangent line, we need to have a slope. But in order to have a slope, we need to be able to take the derivative. So my first job is to take the derivative of this function right here. So I'm going to go ahead and take the derivative of that. So we're going to take the derivative with respect to x of the function x squared plus y squared plus 2y equals 4. And we get 2x plus 2y dy dx plus 2 dy dx equals 0. And we know that we're going to combine like terms. I'm actually going to factor a 2 out of everything. So we would get y plus 1 dy dx equals negative x. And so therefore dy dx, my equation for my slope, is negative x over y plus 1. Okay, well now what I need to do is I need to evaluate the derivative when x equals, let's see, let's not use what x equals, let's use that point. Sorry, the point would be 2, negative 2. So if I evaluate that at 2, negative 2, I'd get negative 2 over negative 2 plus 1. And so that gives me negative 2 over negative 1, which is just positive 2. Okay, well now I have my slope. So now I know my slope and I know my point. So I'm going to go and write the linear approximation. We call it x, L of x. L of x equals the y value, negative 2, plus the slope times x minus the x value. And if you're not comfortable with this, go back to the idea of point slope form, you guys. So we can always do y minus the y value, and the y value is negative 2, equals the slope 2 times x minus negative 2. It's a lot of 2's in this one problem. And then subtract the 2 over. So if you're having problems, just come back to the point slope form, and then you'll be able to get it back into this form pretty easily. Okay, so now it says we want to evaluate it when the x coordinate is 2.1. Well, I may not have known what the derivative of 2.1 was here, but what I can find is now I can take 2.1 and I'm going to substitute it in. So let's do that. L of 2.1 says we're going to do negative 2 plus 2 times 2.1 minus 2. Okay, so we get negative 2 plus 2 times 0.1. So we get negative 2 plus 0.2. So the linear approximation is negative 1.8. Okay, now answer me based on the picture of the graph. Is this an overestimate or an underestimate? This is an underestimate at this point. Why? Because at this point, this part of the graph is concave up. You get to about right here, and this would change to an overestimate. But right now, these numbers are just underneath the curve, and therefore that would be an underestimate. So take this same idea and find when the x-coordinate is 1.9. So hit pause, try it. Okay, well, you guys, we didn't have to really do any work for this one. What I'm going to do now is just plug in 1.9 to the problem that I had, and we get negative 2 plus 2 times 1.9 minus 2, negative 2 plus 2 times negative 0.1. So we get negative 2 minus 0.2. So the linear approximation here would be negative 2.2. Pretty cool how that works, to be able to find any point on that curve, even if it's not easy to find a derivative there. We wouldn't want to take the derivative and plug in 2.1. What if this is the non-calculator part of the test? So we want to be able to use the linear approximation for that. Okay, let's look at another example. All right, this one says if f of 2 equals 3 and the derivative at 2 is negative 2, use local linearization to approximate f of 2.01. So what do I actually need to do here? I need to write the linearization equation. Do I have enough information to do that? I do. I was given a point and I was given the slope at that point. So they already did all the work for me. I don't even know what my function was, but I know that my equation is going to be 3 plus negative 2 times x minus 2. I don't know why I wrote plus minus, but so the linear approximation, well, let's make that a little bit prettier, is 3 minus 2 times x minus 2. Now, if I'm trying to find the approximation at 2.01, I'm going to go ahead and plug in 2.01. And we get 3 minus 2 times 0.01. So we get 3 minus 0.02. So we get 2.98. So the linear approximation at 2.01 for whatever this function happens to be would be 2.98. Now what we would write is that f of 2.01 is equal to approximately 2.98. Remember, we said the notation matters. We know that from our notation, we have that f of x, just as a reminder, let's go back and write it in a different color. F of x is approximately the linear approximation evaluated at x. Okay, so keep in mind, f of x is approximately what we got for the linear approximation. Okay, let's look at how we can impress our friends. What we're going to do here now is we're going to look at being able to calculate the cube root of 70 without a calculator. So in order to approximate the cube root of 70, we need to use the function y equals the cube root of x. And what we're going to do is we're going to use the one point that we happen to know that's fairly close to 70. And the closest number that we know that's close to 70 is when x is 64. So I'm going to go up to this graph and I'm just going to mark this. And this would be, this would be the ordered pair 64, 4, because the cube root of 64 is 4. Okay, so we have our point. What are we missing? Well, we're missing our slope, right? We need to be able to find our slope. So let's go and find our slope. I'm going to scroll up just a little bit. Okay, well, to find our slope, we need to know that the equation we're dealing with is the cube root of x. And to find slope, I'm going to take the first derivative of this, and it might be easier to consider this as x to the 1/3 power, so that when I take the derivative, we get 1/3 x to the negative 2/3, which is 1/3 cube root of x squared, if we wanted to rewrite it. Well, now I need to figure out the slope evaluated at that point. So the slope evaluated at that point is going to be f prime of 64. And f prime of 64 is 3 times the cube root of 64 squared. I would probably take the cube root first. I happen to know the cube root of 64 is 4. So we get 1/3 times 4 squared, which means we get 1/3 times 16, or 48. So my slope at that point is 1/48. So now if I were to write this equation, my linear approximation is, remember in point slope form would be y minus 4 equals 1/48 x minus 64. In the linear approximation is going to be 4 plus 1/48 x minus 64. So now I can evaluate this at 70, and the value of this function at 70 is 4 plus 1/48, 70 minus 64. 4 plus 1/48 of 6. 4 plus 6/48, let's reduce 6/48 to be 1/8. So 4 plus an eighth would be 4.125. So my linear approximation is 4.125. So we would say the cube root of 70 is approximately 4.125. Does anybody want to check your work on that? See what it is? Well, I just typed it in my calculator, and the cube root of 70 is actually 4.1212. So it's a little bit off. Now, let's look at, and let's hope my pencil makes it because it just told me it was running low. Let's look to see if our approximation of a cube root of 70 is an overestimate or an underestimate, or over approximation, under approximation. Let's look at the picture really quick. Sorry to keep scrolling on you. Based on the picture, is it an over or under? Well, based on the picture, if we look at this tangent line, we know this tangent line happens right where this graph happens to be concave down. And we know then it's above the curve, so therefore it is an over approximation. But the question doesn't say that. It says, how do you explain this with calculus? So let's do that. Let's explain it with calculus. With calculus, we need to know whether or not we have a concave up or concave down graph. So we know that if my my original function, f of x, is the cube root function, and my first derivative is the equation we got 1/3 x to the negative 2/3, the second derivative of this would be negative 2/9 x to the negative, subtract 1 would be negative 5/3. Okay? So what I'm trying to show is whether or not at this point it's concave up or concave down. So I'm going to plug in 64 to the second derivative to see if it is concave up or concave down. And if we plug this in, what we get, plug it in your calculator, you'll see that this is actually less than 0, which means what? Well, it means that the original function is concave down at that point. We knew that. We could see the picture up above. But to prove it using calculus, this is what it looks like. So what I know then is that my linear approximation at 70 is actually greater than the function value at 70. Okay? So this tangent line over approximates. So the linear, there's a lot of dots for that I, linear approximation is more than the function value, okay, because the tangent line over approximates. The tangent line over approximates. We could have seen that from the graph, but we can prove it using calculus too, because we know the second derivative will tell us about our concavity. All right, so that is the idea of local linearization. Obviously, there's more things we can do with it. You're going to have a WebAssign assignment tonight to work on linearization. Remember, you could hear three things: tangent line approximation, local linearization, or just linearization. Any one of those three could be used the same. And if you have any questions, feel free to hop on the call, and we will talk to you soon. Have a good day.